Okay, so today we start the lecture 7 for this course, and we would be we have already started discussing what surfaces. So let's just wind back and look at what all we have discussed in surfaces, and let's try to summarize it. So we started with the smooth surfaces, and essentially the idea is to employ calculus, the tools from calculus to analyze surfaces. And we would want the function on a surface to be differential, of course, and that leads us, that gives us a lot of freedom in analyzing the manifolds or manifolds of or surfaces, right? So we had initially begun with discussing defining what the term smoothness for a surface implies. And we learned that if there is a mapping between, say, a subset of Rm, open subset of Rm to subset of Rn or to the Rn space, and we recognize that it's smooth if each of the components of the mapping F happens to be uh, differentiable and differentiable for all orders, right? Now we showed, but in surfaces, what we see is in general, like what we are discussing is that we take m is equal to 2, in a sense that locally a surface seems to be some sort of a 2D object, I mean, or defined by a 2D coordinate space, right? So essentially, what we say about surfaces is that it maps a subset from R2 and the subset of R2, which is U, and it maps to R3 space. And then this F will have three components, F1, F2, F3, all of which will be function of UV, right? Which are just the coordinates in the open subset or coordinates in R, so to speak, R2 space, right? Then we define certain short notations, right? And we talked about what is a surface patch, and when is it regular, and what are the necessary conditions for the surface patch to be regular, and also, uh, of course, we use the idea from the previous this definition of smoothness. And furthermore, we also try to refine it and define something what we call as the allowable surface patch, right? And what is an atlas, right? So we talked about all that. So today, the idea is that we would be moving further ahead in this when talking about smooth surfaces, and we'll discuss a bit on smooth maps and followed by tangents and derivatives, and also on normals and orientability. And we would look at a few surfaces and maybe just define what is the inverse function theorem, right? So that is the what we are planning for today's session, right? Okay, so we have had already talked about the uh, allowable patch and all, right? So let's follow up with an example. So example is that, say, a plane, right? A plane is a smooth surface. And before that, let's try say that a plane is given by plus V into Q vector, where P and Q are unit vectors, right? And are also orthogonal to each other, right? And A is some fixed constant vector, which lies on the plane. So essentially the idea is that for defining something on a plane, right? So, and say we have this as the origin, I mean the coordinate system, X, Y, Z, and let this point be A, right? On this plane. So this is a vector, and then some sigma, which is another point uh, on this surface, I mean on this plane, right? So sigma vector, and the idea is that let's say we have two unit vectors at this point A itself. So this is point A, right? So two unit vectors, say these are uh, P vector and Q vector, right? So the difference, so, and then we have sigma vector. So it says that sigma vector minus A vector will of course lie on the plane. So this will be explained in terms of a linear combination of P vector and V vector, where U and V are coordinates. Now, where does this UV come from? The thing is, when we map, since a surface is a mapping from 2D space, so say you have UV here, and from this U set to the mapping here, right? So which means that U and V are the coordinates in of the subset U, and which gets mapped, say, since this gets mapped to this point here. So let me use a different color. So this gets mapped to this one. So that is what the definition of any wave surface is, right? Now, so let's check about the regularity conditions. So say we have sigma u is equal to partial sigma vector by u is equal to just p vector. Likewise, sigma v is equal to partial sigma by partial u is equal to q vector, right? Just these two. Now, sigma u cross sigma v is equal to p cross q. And this is, of course, not equal to zero vector, right? Since by our choice, p vector and q vector are orthonormal unit vectors, orthonormal vectors. So that's what. And then this would just give us the normal vector to the plane. So this vector, right? So this means it's a regular vector, right? And likewise, let's do take another example of a sphere. So for a unit sphere, say something like this, and with the origin at the center, maybe, or the center of the, sorry, you have a sphere. So at any point, when we draw a line, say parallel to z-axis, and let it intersect the xy plane. So this gives us an angle of right. So this gives us an angle of, say, theta, or let's see, and this to be phi. Right. I hope this is the convention that is typically followed. Just, okay, yeah, this is the convention that's typically followed, yeah, to define a sphere, right? So then, and this is the phi is the angle made by this projection of any point sigma vector on the sphere on the xy plane, right? So this means that sigma vector is equal to, let's define the xy coordinate. So x coordinate will be a function of, and let it be a say unit sphere. So which means that r is equal to 1. So we don't need to worry about the radius. So x will be a function of, say, theta comma phi, and this is given by, uh, say, cosine theta and cosine phi. Likewise, y as a function of theta is equal to cosine theta and sine phi. And then z, of course, as a function of phi theta is given by sine theta. So that is the vertical projection of the sigma vector. Now, which means that our surface patch is a function of theta phi, and it's given by this coordinates cos theta, and cos phi, cos theta, sin phi, and sin theta. Now taking sigma vector u is equal to, in this case it is sigma vector theta, so that is the placeholder for u and v, right? So u is equal to theta and v is equal to phi. So sigma theta is equal to partial derivative, so it gives minus sin theta cosine phi, comma, minus sin theta sin phi and cosine theta. Likewise, sigma v is equal to minus cosine theta sin phi cos theta cos phi, comma, 0, right? And let's take its cross product. So cos sigma phi is equal to, in this say E1, E2, and E3 coordinates. So we have minus sin theta cosine phi minus sin theta sin phi. Okay. And this one will be cosine theta, and we have minus cosine theta sin phi cosine theta cos phi and 0, right? So let's take the to get the cross product. So we have E1 this minus this, so we have cos squared theta and cos phi E1 vector, and plus cos into minus cos squared theta sin phi and 0. So we have E2 plus minus sin theta cosine phi cosine minus sin theta cos square phi, and then we have minus into minus minus, so minus into, so it's minus into minus minus plus, and then into minus again, so we have minus. So we are left with sin theta cosine theta and sin square phi. This is E3. So upon simplifying, what we have is cosine square theta cos phi E1 minus cosine square theta sin phi E2, right? And then minus, so minus sin theta cosine theta is a common, so we have sin theta cosine theta, and then cos square phi plus sin square is equal to 1. So, and what you see is this is not equal to 0, right? So it means that of course if we take the norm, so we will have cosine square, so cosine 4 theta cosine square phi, likewise for the second term, plus sin square phi plus sin square theta cosine square theta. So this is equal to 1. And then inside, you can even have cosine square theta as common. So cosine square theta plus sin square theta. So this gives us cosine theta, the norm of that, right? So that is what it is. Now let's have some propositions, and today we would not be proving that anything much, because we would really want to enter into the operational aspect of surfaces. Yes. So proposition, it says that the transition maps of a smooth surface are smooth, right? Okay, and then the second proposition tells us that say let u and u bar, or maybe you can call it u tilde, be open subsets of R2, and let sigma vector from U2 be a mapping from U to R3 be a regular surface patch, right? And let phi be a transition map which maps from U tilde to U, be a bijective smooth map with smooth inverse map. With smooth inverse P inverse U to U tilde. Then sigma tilde vector from it is a composition of two maps, sigma vector and then composed with phi, which is the transition bijective map, and this be mapping from U tilde to, of course, R3 is a regular surface patch. So it says that if you have two subsets of R2 and sigma is a regular surface patch, then there is and if say we have phi which maps from U tilde to U and it's a bijective smooth map with smooth inverse map, then the composition of sigma and phi is a regular smooth map as well. Right. So a very brief proof is that say this is smooth, right? Sigma tilde is smooth. Right. The reason is because it's a composition. So composition of smooth maps are smooth. Right. Since and phi are both smooth. Right. Now say you have, so let we have UV, of course, and this will be a mapping from phi of say U tilde to V tilde, right? Now the sigma partial sigma tilde by partial U tilde is equal to, so this is going to be given by so at first we can just have that sigma tilde U tilde V tilde is equal to sigma U of U tilde V tilde, right? And then V of U tilde V tilde, right? So when we differentiate this side by U tilde, then this gives on the right hand side what we have to use chain rule. So this one into U by U tilde plus V and then V by U tilde, right? So we can just write it as sigma U and partial U by partial U tilde plus sigma V vector partial V by partial V tilde, right? And likewise, then this can be written as sigma tilde U tilde. Likewise, we have sigma tilde V tilde is equal to sigma U and partial U by V tilde plus sigma V partial V by V tilde. Right? Now, and we can have that so sigma U tilde cross sigma V tilde is equal to, so that it will be the cross product of both of them, right? So it is as if, so this cross this minus this into this minus this into this, right? So what we'll have is u by u tilde, v by v tilde minus u by v tilde and v by u tilde. This into, isn't it? So this is what we call as the Jacobian. So it is the determinant of Jacobian. And where the Jacobian J of phi is given by, so this is the Jacobian of the mapping, right? Of the mapping which maps between two sigma, sorry, u to u tilde, right? So this we have as u by u tilde, and then u by v, then we have u by u tilde, and then this we have as u by v tilde. This one will be v by u tilde, v by v tilde. So this is the Jacobian. And so if say, right, estimate. So if we have say two maps, psi and psi tilde, and let both of them be smooth maps, right? And if both of them are smooth maps, right? Between, of course, between two open sets, between two open sets of R2, then J of psi tilde and composed with psi vector, it can be the Jacobian of composition is just the product of the individual Jacobians. Right? So now if J, so say if we have, if say psi is equal to phi and psi tilde is equal to phi inverse, then we have, so the Jacobian of phi composite phi inverse is just identity, right? So it's identity, Jacobian of identity matrix is just Jacobian, just identity. And this will be equal to Jacobian of phi and Jacobian of phi inverse. Or rather, it's the opposite. So we'll have phi inverse and Jacobian of phi. So we can just have Jacobian of phi inverse. Sorry, Jacobian of phi inverse is equal to Jacobian of phi the inverse matrix itself. So since Jacobian of is invertible, and its determinant is non-zero. So what happens is that sigma tilde is regular, right? Because sigma, as we know, is a regular curve already, right? So even this is regular, right? And so the conclusion here is that sigma, the surface patches. So the conclusion, maybe I should just highlight it in some color. Say, so the regular surface patches sigma and sigma tilde are related, uh, and oftentimes they uh, are, are, so to speak, they are just reparameterizations of each other. Otherwise, that's how we can call it. But maybe a better way of saying is that they are related such that sigma tilde is a reparameterization of sigma, and phi is the of course there are many infinite number of maps, so it is a reparameterization, right? Okay. So now what we will do is let us now discuss about smooth maps. I'll just be giving out the definition, and well, so we come to what are smooth maps. Of course, we had quite a bit of say we have been discussing smoothness for quite some time. So here we would like to say we want to define smoothness between two maps which are which happens to be single surface patches for two different surfaces. So the idea is, let me reframe it. So say two surfaces. Say uh, we have two surfaces, S1 and S2, right? And let them be covered by single surface patches. Sigma 1, which maps from U1 to R3, and sigma 2, U2 to R3. And provided we verify, it's okay. So now, since sigma vector 1 and sigma vector 2 are bijective, so any map F from S1 to S2 gives rise to the map of course, what we would like to we would like to map the domains of both the patches itself. So it's like sigma 2 inverse composed with F composed with sigma 1 vector. And what we'll say is this is essentially just a mapping from U1 to U2, right? And F is smooth. This map is smooth if this map is smooth. So in a sense, this F is smooth if this map is smooth, in the sense that if the transition map is smooth, then even the mapping from the from one surface to another is also going to be smooth. So that is the whole idea here, right? So we'll keep it at that. I believe this explains what we are trying to say. So if this map means transition map. So say we have two surfaces, and say in a special case, or maybe uh, they both have their own reparameterization maps. But say in the special case, what happens is if you can map from the domain of one surface to the domain of another surface, and by saying that uh, as if as if they are related by some sort of a transition map, then even the resulting map from one surface to another is also going to be smooth, since transition map, as we have known from the previous discussion, which is that this reparameterization map is smooth, and therefore this is also smooth. So that we'll keep it at that, right? And maybe just a slight different little. Let me put it here like this. Say we are interested in smooth maps. Smooth maps F, which maps from S1 to S2, of course, and are bijective, and it's smooth, and its inverse map F inverse from S2 to S1 is also smooth. Also smooth. Right? Then such maps are called diffeomorphism. And as we recall, diffeomorphism are uh, homomorphism plus differentiability. Seeability, right? And uh, the surfaces S1 and S2 are called diffeomorphic to each other. Only if such, of course, if such diffeomorphism exists. Right? So we'll have one proposition, and It states that let F from S1 to S2 be a diffeomorphism and if sigma vector is an allowable surface patch on S1, then F composed with sigma 1 is an allowable surface patch on S2. So it says that let this be a diffeomorphism, and then if sigma vector is an allowable surface on S1, then F uh, composed with sigma 1 is an allowable surface patch on S2, right? Right. So the way to prove is that, of course, I'm not going to do it completely here, but since both sigma vector 1 is mapping from U1 to R3 and sigma to there, so the single allowable patch on S1 and S2 respectively. Now, and also F is diffeomorphism. Then F of sigma vector 1 UV is equal to sigma 2 vector of, say, some F of UV, where F is a mapping from U1 to U2, and it's also bijective, as we learned, smooth, and F inverse is also smooth, right? And the rest follows from this. Implies that uh, F is a transition map. Of course, it's transitional. And what we learned in the previous proposition, which is this, that the transition maps of a smooth surface are smooth. So which means that if transition map is smooth, then this implies that FO is also smooth. Right? Since F is a transition map of F O sigma, right? So that's why this is also smooth. It follows from that proposition, right? So now let's begin with tangents and derivatives. So the way we try to understand tangents, right, and or obviously even as surface is so to analyze a surface S, we use, or maybe we examine the smooth curves gamma vector that lie in S. So the thing is, it's very quite straightforward to define tangent for us for a curve, right? So then this the notion of tangent of a tangent vector to a surface emerges from here, emerges from a curve. That is the whole idea. Now let's have a definition. And it states that a tangent vector to a surface S at a point P is an element of S is the tangent vector at P vector of a curve in S and passing through P vector, right? The tangent space TP vector, TP S, where P is the subscript of S at a point P at the point, or maybe at the point P itself, at is the set of all tangent vectors to S at P. Right? Now, following through this definition, let's see. A tangent vector to a surface S at a point P vector in S is the tangent vector at P of a curve in S passing through P. Right? So this is quite straightforward. And the tangent space TP vector, TPS of S at P is the set of all tangent vectors to S at P. Of course, so I think it requires some graphical understanding, right? So the say we have a surface, some surface, and this is our point P here. Now, for this, what can happen is we can have, say, infinite number of um, smooth curves on the surface which pass through the point P. So say this is the surface S, right? So this can be one curve, and the tangent at this will be given by this direction. Likewise, this will be another curve, and the tangent is given by this. Similarly, we can have this as well, and the tangent is given by this direction, right? So at point P, we see that we have gamma 1, gamma 2, gamma 3, and likewise, we'll just have many gammas. So we will be one more gamma. We'll have infinity of such gammas, right? So sorry for the interruption. So we have an infinity of such curves which crisscross, which passes through P, and they all traverse or are contained in the surface S, right? So this is like we have quite a bit of infinite number of such curves, right? So essentially what we have here is that the tangents will have, say, infinite tangents at point P, of course, for the to the surface, but all of them will be contained. You will see that all of the curves will be contained in a plane, which is uh, all of these infinite curves will be contained in this plane, and which passes through P, right? And this is called as TPS. So it's tangent plane of surface PS at the point P vector, right? So this is what it is. Now, furthermore clarification about this is, so let me just note it down, infinite smooth curves through point P, right? And all the tangent vectors, all the tangent are tangent vectors at, or maybe 2s at P is contained in the tangent plane TPS, right? Okay, so to now further to understand this tangent plane, we first choose say geometric understanding maybe uh, of TPS, right? So say we choose a surface patch. Of course, that is the minimum. That's where we begin for a surface, right? We first choose a surface patch which maps from U to R3 of S such that P vector is in the image of S of sigma, sorry. Now, say this point here is equal to sigma vector, say P vector, or maybe say sigma vector at U naught, V naught, U naught, comma, V naught is equal to P vector. So this is, say, P vector is U naught, comma, V naught, right? And if a curve gamma vector lies in S and passes through P vector when T is equal to T naught, say, then there are functions which are ut and vt such that gamma vector t is equal to sigma vector ut and vt, right? So this is what we have as the curve, right? Now, and this is for all values of t close to t naught and sigma vector u naught comma v naught is equal to p vector. Now, if a curve gamma vector lies in S and passes through P vector, when t is equal to t naught. Sorry, I think right for all values close to t naught, right? And this would be u of t naught is equal to u naught and v of t naught is equal to v naught, right? So this is what it is. So of course the functions u and v are smooth, right? And this implies that even that mapping from t to ut comma vt is also smooth, right? It is also smooth. And so this one here, this defines a curve lying in S, right? So this is what it is, right? So which means that that's how we can have given a surface patch and we have the point P and we have the value of sigma vector at u naught v naught and that is equal to P vector. And if any curve lies in S and it passes through P, when for the parameter t is equal to t naught, then we have functions u and v, both of which are function of t, such that gamma vector, which is the parameterization of the curve, and it happens to be given by sigma as a function of u and v, both of which are functions of t. Right. So essentially, that's how we are defining whether the parametric value for sigma or the parametric arguments for sigma in terms of the parameter t, and that's how we are able to say graph a curve on the surface, right? Okay. So with this, we come to a proposition. It states that let sigma vector from U to R3 be a smooth or be a, maybe it's of course a smooth holding. So we have be a patch of a surface as containing a point P vector is an element of S, and let U comma V be coordinates in U, right? So the tangent space to S at P vector is the vector subspace R3 spanned by the vectors sigma u and sigma v, right? So the tangent space to S at P vector is the vector subspace of R3 spanned by these vectors sigma u and sigma v, and of course these derivatives are computed at the point u naught v naught, uh, right? And such that, and this is element of u, such that sigma vector at u naught v naught is equal to the vector p, right? So yeah, so that was the proposition. And the way of saying, like the gentle way of proving is, let's just briefly, sorry, let's just briefly, if we prove this, say we have already known that gamma vector, uh, say in a, it's, say it lies in the surface, say it lies in the surface, and then this is how it will look like uh, notationally. And then say we differentiate with both sides by gamma vector by t. So we have this as, of course, gamma t, and this will be as using chain rule sigma u and then u dot plus sigma vector v and v dot. Right. So what we see is gamma vector. This is a linear combination of this and this. So gamma dot vector is a linear combination of sigma u vector and sigma vector. Right. So what we can say is that right. So so what happens is that any vector in the vector subspace of R3 spanned by sigma u and sigma vector v is of the form lambda sigma u plus mu sigma v. Right? And then for some scalars, lambda and u and mu. Now say if we define the gamma vector to be, say, on that t naught, I mean about u naught and v naught. So lambda t and then v naught plus mu t. So this is how we are parameterizing it. Then we can clearly say that then we see that gamma vector is a smooth curve in S, and at t is equal to 0, that is at the point p vector is an element of S, we have, of course, we can clearly say that gamma vector t is equal to lambda plus mu, and this which means that uh, so this implies that every vector in the span of sigma u and sigma v is the tangent vector, right? So we have, that's how we say that we have infinity of tangent vectors at p of some curve in S, right? Okay. So now, as we know that sigma vector, uh, so the proof ends here. So sigma vector, since it's is regular, so this implies that sigma vector and sigma u vector are linearly independent as well. So this means that the tangent space is, of course, two-dimensional. and hence we of course and therefore we call it as the tangent plane. Right? So tangent space is also called as tangent plane. Now let's try to uh, see what. So we have understood what the tangent space or tangent plane of at any point P of the surface S is defined. So we now move on to understanding what is the derivative. So the idea is now we move to a further, slightly ahead and then talk about uh, what is the derivative of smooth maps or smooth map between surfaces, right? So, so the idea is that given that f from S to S tilde is a smooth map between two surfaces, so the derivative uh, f at a point or derivative of f at a point p vector is an element of S should measure how the point f vector f at p is an element of S tilde changes when p vector moves to a nearby point q vector and say of S itself. Right, so that is the whole idea. So say we are mapping a point P on surface S to some other point, of course, of FP on surface S tilde. Then any point which is nearby, or say if we slightly look at the variation of something or from point P on surface S, then how much will the point after mapping f of P on surface S tilde, how much does it change? So that is where the role of derivative, of course, comes here. Now, if P vector and Q vector are, say, very close to each other, then the straight line through them should be nearly tangent to S at P vector, right? So we should expect that the derivative of f at P vector associates to any tangent vector to S at P vector, a tangent vector to S tilde at F of P vector. So in other words, the derivative of f at p vector should be a map. And what does this map do? So dp vector, dp at of f is a mapping from tangent plane of s at p to tangent plane of s tilde at fp, right? So this is what that's what it is, right? So so in a sense that say let w vector is an element of TPS and it is a tangent vector to s at p vector. Now by definition, w vector is a tangent vector to at p of a curve gamma in S, and it passes through T, and we can call it that, say, W vector is equal to gamma vector at T naught, right? Then, of course, this is also being mapped to S tilde. So gamma tilde is equal to f of gamma vector is a curve in S tilde and which passes through f of p vector when t is equal to T naught. So W tilde is equal to gamma tilde dot at T naught is equal to, and this is an element of TFP at S1 for S tilde surface, right? So with this, we have a definition. So the definition says that, before that, let me just try to give a geometric interpretation of what we are doing here. So say this is our the surface S, maybe a surface patch, if we can call it that way, and let this be our surface S tilde. So this surface S, and there is S tilde, and let this be point P vector, and then there is a smooth map between these two surfaces. So I should just call it like this. Then we have this point F of P, right? And we have a map tangent plane here, right? So this is TP of S. So, and we have a vector W inside. Maybe let me use a different color here. This is the W here. So after mapping, we have, maybe let me slightly. So we have a tangent plane on S. So this tangent plane will be given by T of FP vector and S tilde. And we have this gets mapped to, and suppose this gamma W vector was a tangent vector to gamma T. So this gamma T at gamma T is equal to T naught. And then we have, say, W vector as like this. Right? So we have W vector as like this. And then this gamma vector is like, this was the curve. So this is the gamma tilde is equal to f of gamma, right? And then this is where W tilde. So that is what we could define as the mapping geometrically from one surface to the another of, and that is the derivative of the smooth map between these two surfaces, right? Okay, so let's coming back to the definition. What we meant to say that the derivative dp f of f at the point p vector is an element of S is the map dp vector from S from TPS to T of P, TF of P S tilde such that dp f of W vector is equal to W tilde vector for any tangent vector. W vector is an element of TPS. So that is what it is. So I think that part is clear. Okay, and let's follow it up with one more, or maybe we'll give a slight, I mean, very brief proof. Okay, so say we have gamma tilde, which is a surface patch from U to R cubed, right? It's a surface patch of S, and then P vector is equal to sigma vector U naught V naught, right? Then, or maybe we can call it let alpha beta be smooth functions on U such that f of sigma vector uv is equal to sigma tilde vector of alpha uv comma beta uv, right? And if say w vector, of course, will lie in the tangent plane, so it can be expressed as lambda sigma u vector plus mu sigma v vector, and it is a tangent vector, is tangent vector to P. It is a tangent vector to P for the curve gamma vector, and is a function of T, and then sigma vector ut vt, right? And u and v are smooth functions such that u of t naught is equal to u naught and v at t naught is equal to v naught, right? Okay. Now, say the corresponding curve on S tilde is gamma tilde is equal to u tilde t v tilde s, right? Where u tilde will be a function of alpha t, alpha of uv, and likewise v tilde is equal to function of beta u of t, v of t, right? So now dp of fw vector is equal to u tilde dot u tilde plus, this is of course quite straightforward, and then so this is maybe for a better clarity. This is nothing but the derivative of gamma tilde. of t, right? Plus v dot v tilde sigma, right? Okay. And what we can do is, uh, so uh, in this case, u tilde dot can also be expressed as alpha u dot plus beta u dot by chain rule, right? Or sorry, it's okay. It's alpha u, right? So maybe we can just have it. Uh, so you will be alpha u dot plus alpha v dot, then plus beta u dot plus beta v dot, and then right. So this is what we have, and thus and all the derivatives are evaluated at t naught, right? Okay, so thus we have dp fw vector is equal to, and alpha u dot, as we recall, uh, so u dot is given by lambda here, alpha u, plus v dot is given by mu, and then this we have u tilde plus here the same thing, so lambda beta u plus mu beta v. And then sigma, right? So this is what we have. So what we see is this only depends p vector, because that is the point we are considering, and the mapping f, and of course lambda and u. And this means that ultimately it depends on p vector, f, and w vector. That's it. Right? We will do two more propositions, and we'll move to normals and oriented later. So this proposition says that if f from S to S tilde is a smooth map between surfaces, and p vector is an element of S, the derivative dp vector of f from TPS to TF of P S tilde is a linear map. And this the proof follows from here itself. Let's bring this copy paste, right? So the idea is that if f to f is a smooth map between surfaces, and then the derivative of dp from this is a linear map. Okay, so the way we have is the basis of TPS is sigma u and sigma v. Likewise, the basis of TF of P S tilde is sigma tilde U tilde and sigma tilde V tilde. Right. So what we can have here is that so when we have a mapping from okay, so let's try to have it in this fashion. We'll have one say we have lambda mu and then alpha u, alpha v plus lambda mu, likewise beta u, beta v, and then this we can construct as if and actually since it's the other way around, since we are mapping from TPS to TPS tilde, we could reformulate this in terms of some input argument, right? So right hand side, we want to have as some sort of an input. So we can just write it as sigma u tilde, this one, as alpha u, beta, alpha u, alpha v. And we're just looking because that's how we want it to be. Plus sigma tilde, v tilde of beta u, beta v, and then lambda u. So that's saying that we have lambda u as a input parameter, right? An input parameter to this mapping, isn't it? So right, and so what we can rewrite this as is in this fashion, that is a matrix and they are column vectors. And then this we can call it as alpha u, alpha v, and beta u, beta v. This is alpha v. And then on the right hand side, what we have is lambda u, mu. And we can see that it should give us the same same expression where we had started. Like this is what it should be, right? So what we see is that lambda mu are defined in sigma u and sigma maybe is defined in this vector basis, right? In this, it's defined in this basis because they're essentially the components of some vector w in this basis, right? And these were the components of w in these two bases, and then we had mapped it to such a form here, right? So we are mapping it to the components in. So from this, we can clearly say that this is the linear map, or maybe this is the Jacobian matrix of the mapping. So this is the Jacobian map, Jacobian of the mapping. It takes the components from sigma u v sigma v basis and then maps it to sigma tilde u tilde and sigma tilde v tilde. Right. So that is what it is. So therefore, smooth map is smooth map we have is uv, and this is the Jacobian of the smooth map uv2 alpha uv beta uv. Right. So there's one of very useful thing here, and let's have one more proposition before we start normals and orientability. And this would be just a definition, the way I will be putting it here. So it says that number one, if S is a surface and P vector is an element of S, the derivative of P of the identity map of the derivative of P at P of the identity map S to S is the identity map TPS to TPS. Right? This is of course trivial, but anyway, it helps as an identity, right? The second thing is if S1, S2, and S3 are surfaces, right? And F1 is a smooth map from S1 to S2, and F2 is a smooth map from S2 to S3. Smooth maps. Then for all P vector is an element of S1, B P vector of F2, F1. This is equal to D F1 P vector F2 of composed with the P vector of F1, right? And the third point is if F from S1 to S2 is a diffeomorphism, then for all P vector is an element of S1, the linear map dP vector F from TP vector S1 to TFP vector S2 is invertible. Right. So this was the definition. We all, for proof, please look at like please refer to Presley's book for proof. Right. Okay. So now we begin with normals and orientability. Right. So in this, we know that the tangent plane TPS, right, of a surface S at any point or at a point P vector is an element of S, passes through the origin, right? And it is completely determined by giving a unit vector perpendicular to the plane, and it's called a unit vector, called a unit normal to S at P vector, right? And what we say is that, say any surface we have, and this is the tangent plane, then there are two normals. One normal will be coming outside, the other normal will be going down. So we have two choices. Two choices for normal. Right. So this is normal one, normal two. We can just call it as a normal plus and then normal minus, right? Now the issue is we have two such normals, right? And now if we have, so we have two choices for normal. However, say if we choose the surface patch, say sigma vector from U1 to U2, U1 to R, U to R3, and containing P vector, then we can define the unit normal vector to this surface patch to be simply sigma U cross sigma V by norm of sigma U cross sigma V. This is an obvious choice. So this is what we call as the standard. So all derivatives evaluated. So this is the standard unit normal of the surface patch. Right? Surface patch sigma vector at the point on the surface P vector. However, what we see is that in the case of tangent plane, we have a unique tangent plane. But say, like, unlike tangent plane, n vector is not quite independent, What? Of the choice of patch. Sigma containing that is the issue here, right? And it's not quite independent. Now, in fact, what happens is, in fact, if sigma tilde is a mapping from U tilde to R3 is another surface. another surface patch in the atlas of S containing P. Then what we have is that we had seen that sigma tilde u tilde cross sigma tilde v tilde is equal to determinant of the Jacobian phi and sigma u cross sigma vector v. And so this is the Jacobian of mapping of Jacobian of transition map, right? That is what it is. And this is map phi from sigma 1 to, or maybe, sorry, it's a sigma to sigma tilde. So what happened here is that, so the choice is that the issue that we face is that n tilde, n gamma sigma tilde is, so we have n sigma tilde cross, sigma tilde u tilde cross sigma tilde v tilde by norm of sigma tilde u tilde cross norm of sigma tilde v tilde. And then we can put it as determinant of J of phi, and then sigma tilde cross u sigma u v sigma v divided by the determinant of J phi, right? And sigma u cross sigma v, the norm. So this will be determinant of Jacobian of phi divided by the magnitude of determinant of Jacobian of phi. And sorry. Then this becomes just sigma u cross sigma v divided by the norm of sigma u cross sigma v. So this is, of course, clearly defined as n sigma. However, this one, if the determinant, so this is equal to, or this is greater than 0, if determinant of J, so not greater than, I mean, just call it is equal to 1, if J of phi is greater than 0, and is equal to -1 if determinant of J is less than 0. It's something, some sort of a sign function. Actually, it is the sign function, right? So which means that therefore the sign, so remember that we can have that this implies that n sigma so the idea is that this will be n tilde will be equal to plus minus n sigma, right? And where this sign is determined by or of course actually the sign is the determinant. If we see that if this is the determinant of J phi. So based on this, we define the following definition. So the definition goes that a surface S is orientable if there exists an atlas A for S, atlas A of S with the property that if phi is the transition map between any two surface patches in A, then determinant of J of phi greater than 0, where phi is defined. So it says that a surface is orientable if there exists an atlas A with the property that if phi is the transition map between any two surface patches in A, then this determinant of J of phi has always to be greater than 0. So that is the that's what we are looking for here, right? So after this, we'll have a proposition where we talk about furthermore in this about this orientability. Okay. Okay, so the proposal says that let S be an orientable surface equipped with an atlas A, right? Then there is a smooth choice of unit normal at any point of S. So this means that they can take the standard unit normal of any surface patch in A. So the idea is that if S is an orientable surface, it has its atlas A, then what we can have is then there is a smooth choice of unit normal at any point of S, right? And when then we just take the standard unit normal of any patch in surface patch in A, because the thing is, since it's an orientable surface, right? So the determinant of J is always going to be greater than 0, and J of phi. So which means that the sign of is well defined, sign of the rule, sign of the unit normal, right? So based on this, we note this down that an oriented surface an oriented surface is a surface together with surface S together with a smooth choice of unit normal n at each point. That is a smooth map n vector from S to R cubed, right? Such that for all P vector is an element of S, n vector as a function of P vector is a unit vector perpendicular to DPS, right? And any oriented surface any oriented surface is orientable. Of course, that is true. That is obvious, right? So the way we do is that we start with a maximal atlas of S, and we only retain all those patches, sigma UV, if sigma U cross sigma V is a positive multiple of n at all points in the image of sigma vector. Otherwise, we discard it. So we first construct a maximal atlas using the maximum possible atlas for that surface, and then we only choose all those allowable patches, which for which sigma cross U vector is just a positive multiple of n, which we have already chosen from when we define it, right? And throughout this course from now on, we would be dealing only with oriented surface. So this is a very important point, so I'll just mention it. we shall only deal with oriented surface, right? And also we shall use only we shall only use surface patches for S whose standard unit normal is the same as the chosen normal of S. So we have to first choose a unit normal, right? And then based on the requirements, and then we shall look at all the surface patches which have that unit normal, right? Which preserve the sign of the unit normal such that the unit normal happens to be smooth, right? Okay. So with this, we just provide some examples of surfaces. Maybe I'll just have it in the next. Some examples of surfaces. So we start with level surfaces. So level surfaces are given as the form is the general form is x, y, z is an element of R3 such that f of x, y, z is equal to 0. So, and where f is a smooth function. That okay. So just one theorem in this regard. So it states that let S be a subset of R cubed with the following property. It's for each point P vector is an element of S. There is an open subset W of R3 containing P and a smooth function F from W to R such that S is equal to X, Y, Z is an element of W such that right. So this is it. And number 2, the gradient grad of F is equal to Fx, Fy, and Fz, where X and YZ are the super subscripts of F, and F does not, gradient of F does not vanish at P vector. then S is a smooth surface. Right? An example is, say, an example for this is when we describe a sphere, right? Say one such example is for a unit sphere. Unit sphere. So in this case, we write the form of the surface as equal to 1, right? So ideally, this will be, it has to be a form of x, y, z is equal to 0, right? So x squared plus y squared minus z squared is minus 1 is equal to 0, right? And then the grad of f in this case, so unit surface, and then we have W can be equal to R cubed, right? W can be of R cubed, right? And grad of F is equal to 2x, 2y, 2z, right? So this implies that norm of grad of F is equal to say 4x squared plus 4y squared plus 4z squared, the square root of that gives us equal to 2 into root over x squared plus y squared plus z squared, which is just 1. So we have 2. And this is at all points in sphere. Right? So which means that grad of f is non-zero on S2. This implies that S2 is the unit sphere. That's how we write it. So S2 is a smooth surface. Right. So the next one such example of surfaces are quadric surfaces, and this is in itself a huge chunk in surfaces. So we would just leave it at quadric. We call it quadric surfaces. So we'll just give you a very basic definition of that. So the definition of such surfaces go as a quadric is a subset of R3 defined by an equation of the form vector transpose A V vector plus is equal to 0, and where V vector is equal to x, y, z, and A is a constant symmetric 3 cross 3 matrix. B vector is an element of R3, is also a constant vector. And finally, C is an element of R, is a constant scale. Right, so this is what we have. And there are several examples. One example is even the previous case, the sphere is also an example. So examples, let's look at some examples. So say x squared plus y squared plus z squared is equal to minus 1 is equal to 0. So this you can write it as like this. So we can have x, y, z, and then here also and this will be again x, y, z plus, so it will be -1. This we can write it like this, right? So there is no linear terms in x, y, z, so the coefficient is 0, or b vector is just a 0 vector. And for a, what we have is there is no cross coupling. So there is no cross product between x, y, and z, right? So it means that all the off diagonal terms will have a 0. Right, so we are left only with diagonal terms, and then we see that even if it's xx, so there is the multiplicative factor, the coefficient of x square is just 1, so we have 1 here. Likewise for z, y, and for z. So this is c. This we can recast in such, and say even if we have something called as a ellipse, right? Ellipsoid, then x squared plus y squared plus y squared plus by q squared plus z squared by r square is equal to 1. So this you can write it as -1 is equal to 0. So this is sphere, and this is ellipsoid. So in the same fashion, we can have x, y, z. This x, y, z. There is no cross product. I mean, there is no linear term, so 0, 0, 0, x, y, z. And this becomes -1 is equal to c. And no cross terms, no cross product terms. So we have this. So the diagonal terms will be 1 by p square. And in this case, 1 by q square, 1 by r square. So these are such examples, right? Okay. And finally, what we have is the ruled surfaces. And we would talk about it further again, but just as an introduction. Ruled surfaces and surfaces of revolution. So what we have seen is that the ellipse, sorry, maybe cut and then paste it. So what we have seen so far is that all these surfaces, what we have talked about, they were all algebraic in origin, that we had to clearly specify x square. I mean, the explicit form of explicit form, in its explicit form, we had to define the x, y, and z coordinates uh, of the surface, right? However, this may not be possible in general. So, and there are many such classes of surfaces which can be constructed using geometry. So from we utilize the geometric some of the geometrical properties that are inherent in those surfaces to construct them. So one such example is what we call as the ruled surface. The ruled surface is a very interesting surface in that they form some of the part of slender structures as well. If you look at uh, say plates, sorry, plates, even, yeah, plates and ribbons. So they are all an examples of ruled surface, and even what we very famous structure called Mobius band, that's also a ruled surface, right? So that is where we see some of the uh, uh, practical scenarios of a ruled surface, right? So mathematically, we define a ruled surface is a surface that is a union straight lines called the rulings, right? or sometimes the generators of the surface. So it's a surface that is a union of straight lines, which are called rulings or sometimes generators of the surface. And I hope you may recall that from the school years that the outer line, right, which joins the apex of a cone uh, to the base circular base circle is what we had called as generators. So the thing is, even the surface of a cone is also a ruled surface, and that we'll see it from. I mean, just let's discuss it now. So initially, let me just briefly. I mean, let's first have a geometry. So say we have this curve, right? So this is a curve which is parameterized as gamma. And then we have these ruling straight lines. At every point, actually. But the thing is, yeah, of course, we cannot, there would be infinity of such straight lines. So let's just extend one for demonstration purposes. So we have this point, Q vector, which lies on the curve. So there is a curve. And they collectively form a surface. So there is a surface. So this is a surface, right? There is a surface. So you have Q vector here and some P vector. Here's some P vector. And this direction is given by delta vector. And along this curve, let us have a parameter called, so along this curve, U increases. So we have U goes like this and V goes like this along the lines. So here you have some UV, which means that I would call it, to be more precise, UV. So this point maps to this point here from some sigma vector. And this is the U set U that we discussed from the, that's how we define our paths, right? Okay. And you have this delta as a function of U because this delta vector will be a function of U. Now, let's write it down. Suppose C is a curve. So this is C, right? So C is a curve in R3 that meets each of these lines. Right? And any point P vector of the surface lies on one of the given straight lines. Given straight lines. Now this intersects C at Q vector, right? Now if gamma vector from alpha to beta to R cubed is a parametrization of the curve of C with gamma vector U is equal to Q vector, and if delta vector of U is a non-zero vector, in the direction of the line passing through gamma vector u. Then g vector is equal to gamma u plus v of delta vector u. So v is where, so this we had uv, right? So ideally this should be, this point will be mapped to uv. Sorry for the confusion, because this q will be actually parameterized as, so this point here, any point on the u axis, this point gets mapped to here on the center line. So it means that this part is contained on the surface. So u axis is contained on the curve gamma vector, right? Okay, so you have p vector is equal to gamma vector plus v delta for some scalar v. Now, and we can of course this denote as sigma vector u v, right? Now, so sigma vector from u to r cubed is a smooth map, and where u is equal to uv is an element of R2, right? So and then alpha is less than u is less than beta, right? Now, moreover, say denoting d by du by a dot as it resembles that of parameter t, right? It resembles that. So sigma u is equal to gamma dot, of course, plus v of delta dot of u, delta dot, right? And then sigma vector v with partial derivative of sigma with respect to v gives us delta vector u. Now, therefore, sigma is regular if sigma u cross sigma v is not equal to zero vector. Right? Now, which means that this implies that gamma vector plus v delta vector and delta vector are linearly independent. Now, this would happen only if, so this will be true. This is true if so this is true if gamma vector and delta are linearly dependent, and v is sufficiently small. In that case, it will be. So which means that therefore, it implies that to get a surface, to get a regular surface, C, the curve C must never be like the curve C must never be tangent to the rulings, right? Because otherwise, what happens if C is tangent? What happens is now since so that say delta U, if say gamma dot is equal to tangent, then it will be parallel to some k into delta vector. And this implies that at the point P, what will happen is this implies that gamma dot cross delta vector is equal to k delta cross delta is equal to 0, right? So that's the reason we cannot have C to be tangent. It should always be at, like its tangent should never be parallel to the rulings. Now some examples, let's have some examples of such rule surfaces. Is number one is all rulings are parallel to each other or parallel to each other, right? Then the surface S is called a generalized cylinder. Right. So in this case, what happens is we will have some sort of like this, right? Some sort of a and then so all the rulings, right, are parallel to one another. So this ruling, see all the rulings are parallel to each other. Right? And then you have gamma vector in this fashion. And these rulings are all a vector parallel to it. Right? So in this case, we define our mapping as sigma uv is equal to gamma vector as a function of u plus v a vector. That's it. As simple as that. Right? And what happens is one example, another example is say all rulings make a constant angle with some axis, some fixed axis. So in this case is what we have a cylinder that cones. So we have such this axis, right? And all the rulings, this, 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 right? They all happen to be making some angle, right? With respect to some, this is the axis, this is the fixed axis. And then we have all this. And there's our gamma vector, of course, as a function of u. And then uh, these are the rulings. And we need not have a constant angle, but say if it's a constant angle, then we will have a circular cylinder, I mean circular cone. Then we'll have a circular cone. So fixed angle is say some alpha, right? Then it will be a So this has a circular cone. Okay. So now we'll define one what we call as the surface of revolution. I'll just briefly define, will not talk much. Right. So this we can highlight in terms of surfaces of revolution. Right. So a surface of revolution is the surface obtained by rotating a plane curve called profile curve around a straight line. Around a straight line in the plane. Right, surface geometry is the surface obtained by rotating a plane curve called profile curve around a surface line in the plane. Right? And the circles obtained by rotating a fixed point right, on the profile curve around the axis of rotation are called the parallels of the surface. The surface. And the curves on the surface obtained by rotating the profile curve through a fixed angle are called its meridians. Right. So the ideally what we are trying to convey here is that say you have this as the some axis z, right? Maybe let's make it dotted so that we can, because it lies within the surface, right? So we have some say profile curve. So say we have this x, y, z. This is x and there's y. It's x, right? And say we have some profile which lies on xy plane. Oh, sorry, it lies along say yz, right? In the xz plane. Say it lies in xz plane. Right? So say it lies in xz plane. Now So this is the base profile. Now what we do is we rotate it in the about the z-axis. So we rotate it about the z-axis. So we have so this is another circle, right? This will be some sort of a right. So these are all surface. These are all curves. I mean, these are called meridians. So we rotate it in this fashion, right? And say this makes an angle. So at any point, right? So this any point, this will make an angle, say V, with respect to the x-axis. So this is say one such point. So this will of course not be visible. So we'll have in this fashion. Sorry. So this will our right x-axis and likewise y-axis. And we have any 2 points. So this and these 2 points, right? So about these points will form what we call as the parallels. That's fine. Likewise, the other side. So these are this on this curve is base curve is parameterized as gamma vector of u, right? And v vector is the angle made between this. So these are parallels, parallel, and this is meridian, right? So the way we would like to portray this is so the base curve. I'll just give the basic definition. So the base curve, and it is rotated about this axis, right? It will be here. So the base axis, the base curve is given by gamma vector u is equal to f of u and 0 g of u, since it lies in xz plane. And this is a parameterization of base or profile curve. And the parameterization of the surface, or maybe the surface patch, essentially. The surface patch is given by sigma vector u comma v is equal to f of u cosine v, and then you have f of u sine v comma g of u. So that's what it is. And we can construct anything, right? Circular cylinder, even a cone happens to be a surface of revolution, right? And then we end this section with today's discussion with just the inverse function theorem. I'll just list it down without going further into the, I'll just list this inverse function theorem. So it says that let f be a mapping from u to Rn, and it to be a smooth function, smooth map defined on an open set, an open subset U of Rn, right? And then n is greater than or equal to 1. So assume that at some point x0 is an element of U, the Jacobian matrix F is Jacobian matrix J of F is invertible. Right. Now, before this, we may have to define what is a Jacobian. So it goes as, suppose F is a mapping from U to Rn is a smooth map where U is an open subset of Rn, right? And if we write U1 tilde U2 tilde say till UN tilde and is equal to say f of U1 till UM, then the Jacobian matrix of F is J of F is equal to so partial U1 by tilde by U1, right? And then likewise you have partial U1 tilde by U2 to partial of U1 tilde by UN UM, likewise U2 by U1 U2 by U2, likewise U2 by UM. Similarly, we have U1 and U tilde N. So so we have defined Jacobian now. Then there is an open subset. So there is an open subset V of Rn and a smooth map G from V to Rn such that the qualities are that the properties are that y0 is equal to f of x0 is an element of V, and number 2, g of y0 is equal to x0. 3, g of V is a subset of U. 4, GV is an open subset of Rn. And 5th is that f of g y is equal to y for all y is an element of V, right? And in particular, G from V to R GV and F from GV to GV are GV to V are inverse bijections. So the conclusion of this theorem is that thus the inverse function theorem says that if J of F is invertible, at some point, then F is bijective near that point. So let me just yeah, it's bijective near that point, and its inverse map is smooth. Right. So that is, and the proof can be found in any book on multivariate calculus, and I believe it's something which can be done on your own, right? So with I think with this we end session for today, and in the next session we would be starting with we will define a very special ruled curve, ruled surface, what we are known as the Mobius band. And then we'll get set with discussing about first fundamental form. And we will try to cover as much as possible. And if we are able to do quite a bit, then we will move on to we'll introduce the second fundamental as well in the next session. So I'll just stop recording.